All right, what I want to do is show you the Rust demos, R10 and R20. So let's go to Projects. Everything we've been doing here is pretty much buffer overflows and other things like structured exception handler overflows. By the way, a student asked me to explain structured exception handlers in memory better, but I didn't get a chance to research it, and I'm not ready for that yet, so hopefully by next week. Here's the Rust things I want to talk about now, though. And so you can do it on Debian 10 or Debian 11. That's what I'm using now. You just install the Rust compiler, and it will compile Rust code. So let me bring up my Debian machine here and shove these instructions to the side. All right, make this bigger. Oh, not that one, this one. All right. All right. So here's my Debian 11 machine, and all right, so there's the way I'm doing this. There are other ways to do it, but this is what I learned from some tutorial, is a sort of modern technique where you use a folder for every app. Then in case your app is of a reasonable size and contains many files, although none of our apps are going to be that complicated. So there's this directory called Hello World App, and in there I made my source code hello.rs. And if I look at that, this is print world. Just a function main and then print line Rust says hello. So it looks pretty much like C or Python and so on. So that's a simple program that just says hello. And you compile it. You go into a directory and put your source code in there and then compile it with Rust C. And that creates this executable that you can see there, and you can run it. All right, and so that's just hello world. So you got the compiler working and such. So let's try this. And I make a directory for an integer app here. And then I move into there and put in source code. And here's the source code that makes a few integer variables. All right, so it's going to let I equals 1 and j equal -5. Now you can specify, if you don't specify what type of variable you're making, it chooses a default, or you can put a colon and tell it what type of variable, and this is an unsigned 32-bit integer. And then it's going to print them out. So let's compile that. And notice, it won't let you do it. You cannot assign an unsigned integer to be negative number. It won't let you do it. This is a good thing. Notice how in C, we would do things like make a buffer that can only hold 100 characters and then put in 300 and it wouldn't say anything. Rust won't let you get away with this stuff. All right, so now let's try adding numbers. So let me go up here again to my root directory and clear. Oops, it's not listening to me. All right. And I'll make a directory and make another source file. Okay, so this is going to add some numbers. So all right. So I let a equals 1, and then a equals a plus 1, and then I print whatever it is. So let's see what this one looks like. We compile it. And again, there's going to be an error because that variable is immutable. This is also true of Python and Go. You can declare immutable variables that cannot change, and then you can't reassign them. So there's a tutorial to look at, and there's a couple of flags you can find to debug these programs. But let's get to the more interesting stuff. Let's start with C. So I'm going to go back up here and clear. Okay, so let's make a C integer overflow. So ovc.c is here, and here's the code. All right, so I assign a variable unsigned character, and then I assign it to a number. So this is a single byte character, it only can hold numbers up to 255. I put in 230, and now I make a loop to try to add more to it as I go ahead here. So let's run that. And I compile it with GCC, because that's a C program, and then I run it. All right, and so you're probably used to this. I add 231 and make it bigger and bigger, bigger. When you add it too high above 255, it rolls over like an odometer and turns into 2. Now, you might be used to this by now, but realize how insane this is. Let me put my source code up there. I took a variable and I added numbers from 1 to 10 to it. How is the developer supposed to know that taking a number like 230 and adding numbers like 10 to it is going to produce small numbers? This doesn't make any sense at all. And of course, it confuses programmers, and they make this mistake all the time and lead to vulnerabilities. And I would say it is cruel to write a language like this that confuses people. If I take a number and I add something to it, how could it get smaller? This is what leads to all these problems, and it doesn't happen in Rust. Rust is a less cruel language that doesn't inflict upon you that sort of madness. So we're going to make the same program in Rust. So make a directory. We create this overflow program in Rust. And here it is. Here's the same thing. Notice I made a mutable variable this time, x, and it's an 8-bit unsigned integer, which is what I had in C, a number that can only go from 0 to 255, and I put in 230. Now I have a for loop, and I keep adding those numbers, so we'll see what happens when you run this in Rust. All right, I want to make my window a little smaller because I'm not seeing the stuff at the bottom I should see. All right. Anyway, so now let's compile it and run it. And notice what happens. It gets bigger, bigger, bigger. And when you try to make it bigger than 255, instead of just creating the wrong answer, it stops and gives you an error. Attempt to add with overflow. This is much, much healthier. Your developer will be warned you have tried to put a number that's too big in a variable that's not big enough to hold it, and instead of not telling you and getting the wrong value and shipping it and creating a bug, it will crash and tell the developer you need to deal with this. You need to use a different variable type or cope with this somehow. Much healthier. So that's one vulnerability that you wouldn't have if you were using Rust. And now let's try the main one we've done this whole class about, string overflows. So first we'll start with a string overflow in C. So here's one. So I define two strings. This one is 4 A's, this one is 4 B's. I print out the address. Now I read a new value for one of the strings from input and then look at them again. So let's just compile that, which is here. All right, and then it warns me, by the way, just things like implicit declaration. That's not important. It's a missing header thing. Doesn't really matter. Oh, I missed the include standard IO. Let me actually fix that. I'm surprised it would even let me do that. I missed the first line of code. I don't think it's going to work without that. All right, let's try that again. See if I can compile it now. Okay, now it compiles without complaining. So let's run it. Okay, so if I give it 8 C's, now, okay, so again, let's put the source code out there again, which is st.c. Okay, so now the developer wanted to have one string 4 characters long and another string 4 characters long. Now they read the second variable. And when I put a value in the second variable, it changes the first one to be 3 characters long and C's. Yes, you can use a debugger on Rust. GDB works fine. So anyway, think again about how cruel this is to the developer. I tried to change variable 2, and for some reason, it changed variable 1 in addition to variable 2. How is the developer supposed to understand this and write code without going insane when you input into one variable and it changes a different variable? And of course, they can't. It's too confusing. They often make this mistake, and you have all the string overflow vulnerabilities. So let's do it in Rust. So here we are. We're going to make the same program in Rust. So it defines mutable strings, 4 characters long, and then you read a new value in for one of the strings. So we'll save it. And now do Rust compile. And I'm going to put debugging information here, but -G. And so, by the way, it tells me this variable does not need to be mutable because I never use it again, but that's a warning. That's not, you can still put up with that. And so now we run it. And so notice I have a 4-character variable here and a 4-character variable here. Now I'm going to put in 8 characters. And what happens? String 1 changes to, it keeps the old A's and it adds 8 more C's to it, which is a little strange, but that's not terrible. And string 2 does not change at all. So this is what you want. If I add new data, it appends it to the existing data, but it doesn't go and change the other string because that would be insane. And notice it doesn't have any problem taking something that was defined to only be 4 characters long and then making it longer. It will just handle it. And in fact, you can see that. We'll use GDB to see it. Here's a question about that. Right on target. So let's do GDB -Q on string. This is the Rust program. And list to see the source code because I compiled it with source code. So there's the Rust source code. And so now line 7 is where I input the new value. And that's where I want to break. So I'll break at 7. Okay, and now run. Okay, and so now it tells you where the strings are. This string is at DF90 and this string is at DFA8. So I can examine them. Let's get that in the clipboard, an x/2x, that address. So here's one of the strings. And if you look there, you see the letters are not stored here. Remember, what was stored there was 4 capital A's. So I would expect to see 41, 41, 41. But that is not what I see here. This is a memory address in 64-bit code, 5555. These 64 bits are memory address. That's where the string is. And if I print S1, it will show me, here it is. Here's that address, 69D0. Here's the pointer to it. That's what's there. It's a pointer. It's not the actual data. All right, and now if I continue, I'll put a break on line 10. And I'm going to, S1 is what I'm going to input into, so this is good. I knew where S1 was. It was at A69D0. Now I run, or continue rather. I don't know what's going on here. Okay. And now I put in 8 C's. And now I hit the breakpoint. Now let's print S1 again. Now, the string is still at the same location, but it hasn't overwritten string 2 anyway. And so let's run it again and make it longer. Run. Yes. Print S1. Print S2. So that's where they're stored, 69D0 and 69F0. Now I run it. I continue it. And I put in a lot of characters. 30 characters. Now if I print where they're stored, S1 has now moved. When I put in too much so it wouldn't fit, it just silently moved the variable to a different location, which is what it should do. S2 is still at the same location, 69F0, but the one I changed moved from 69D0 to 8A20. So if you put in too much data, Rust will just reallocate enough room somewhere else and move the variable up there, which is much better, much healthier. So you cannot have a buffer overflow. It will just make the variable bigger as needed to hold whatever text is going in there, and that's what ought to happen. So that's why people are switching to Rust. It's a Firefox developed language, and Microsoft is strongly considering writing parts of the Microsoft operating system in Rust, and a lot of people, and part of the Linux kernel too, they want to write in Rust, as people learn that it's really a whole lot safer. All right, and there's a command injection here too. Let me take a look at the second one. I think it's probably enough of this one. Let me see if, here we go. Dangling pointers and memory leaks. Yeah, let's try heap overflow. So I'll go up here and make a heap overflow in C. So here it is. I declare with malloc, I reserve space on the heap for 20 characters, name 1 and name 2, and then I read it from the input, name 1 and name 2. So let's run that. And compile it. And run it. All right. And so I put in 20 characters. And then 20 Bs. All right. And so, since there was room for 20, I get A and B, and there's no problem. So that's good. Now, let's do it again with 40 characters. I run it, and I'm just going to copy and paste this twice to make it big enough. There's 40 A's, and the same here, 40 B's. And now, the addresses remain the same. Name 1A has turned into 40 A's followed by 40 B's. And name 2 has turned into some horrible mess, pretty hard to read. And so the point is, everything turns into bizarre nonsense. The overflow hits the metadata, so the link between the chunks are corrupted, and you just get garbage. So this is, again, cruel to the developer. You input strings into a string variable, and your stuff gets memory corrupted and turns into junk on you. And again, this will not happen with Rust. So, you can do it in Rust here. So this is how you make it go on the string with this box stuff, and then you can read input from standard in to read them in. So it's very much like C code. And so if you compile it and then run it, all right, if we start with 20 characters long, and then 20 characters here, it works. Name 1 contains this, name 2 contains that. Nothing bad happened. All right, so let's try it with 40. And it works. The first one is 40 characters, next one is 40 characters, nothing bad happens, as you'd expect. It automatically moves things around, and we can examine the stored strings. So if we use the debugger here and list all right, there's the code. So I put a break at 14 just before it prints the last line of data. All right, and then run it and give it 20. Okay, now I can print name1, and I can print name2. All right, so there they are. This is at D0 and that's at F0. So this is fine. They're 32 bytes apart. That's what 20 is. If the display starts looking fuzzy, just refresh your browser. That usually clears it up. And so if you want to see, these are pointers, however. So if you want to see how the strings are stored, you can see where they're actually stored by printing star name1. And that will show you, this is the pointer, and the actual strings, and you'll see the real addresses. Let's do name2. There. The pointers are stored at D0 and F0, and the actual strings are stored at 20 and 40. Again, only 32 bits apart, 32 bytes apart. So that's fine, but so now if I put in characters if I put in 40 characters, it will not be able to continue storing them in locations so close together. So let's just run it again and put in 40 character strings, which I'll copy from the instructions. There's 40 characters, and there's 40 characters. All right, and so now let's print name1 and name2, star name1 and star name2. Again, this is at D0 and that's at F0, but that's where pointers are stored, and now the actual data is now stored at 20 and 60. It has moved the pointers to make a bigger gap here. Instead of 20, which is 32, the gap is now bigger, 40, which is 64, so it has enough room to store the bigger strings. So again, Rust rearranged the memory as needed to accommodate the data. It did not just overflow and corrupt things. How we are getting from D0 and F0 to 20 and 40, 60. All right, these are hexadecimal numbers. D0, it's 16 to get to E0, and another 16 to get to F0. So the difference between D0 and F0 is 32. And the difference here between 20 and 60 is 4 16s, so that's 64. That's all. And you see it's, so when it needed room for 20, it chose to leave a gap of 32, which is probably just having enough for the metadata. Or else it's rounding things off. Yeah, that's all. Yeah, this is, of course, hexadecimal, and you have to get used to that. But anyway, this is, again, Rust saving you from the overflow. All right. And really, I think that's enough. There are a few other things in the project and flags to find, but these, I think, are the main reasons why everybody's pushing Rust. Programmers like it a lot better. As you can see, if you write a program in Rust, you will not be horrified to discover that it does horrible things. It will warn you. If you try to use the wrong variable, make it too big, make it too small, it will either handle it smoothly or warn you. You will not discover that you've fallen down one of those booby traps that she lays for you. All right, I'm going to stop this video.